Okay. Okay, so I'm going to go over a couple of the questions where you didn't have to solve anything. So this is just understanding what is happening to the object when you spin it around in a circle. Okay, so let's look at the one that says you twirl or whirl a yo-yo around your head in a horizontal circle. Okay, so the fact that it's saying horizontal circle is very important. You're not doing a vertical as if you're waving a wand. We're going around like a cowboy, a lasso. So if you look at the picture from the notes that you see here, this picture is going to help you understand the directions that force, velocity, and acceleration are going. Okay, so we have a yo-yo. We're turning it around on top of our head. What direction must the force act on the yo-yo? And we ignoring gravity. Well, let's go back to the picture. And what do I say about the force? The centripetal force is also towards the center of the circle. That's it. It's going towards the center. Next part, what is giving off the force? So that's saying, what is this yo-yo attached to? What is giving that yo-yo the force? Yes, we're spinning it around, but the yo-yo is attached to the string. So the string is giving off that force. Then if part C says if you let go of the string on the yo-yo, which direction will the toy travel? Well, let's look at the tangent arrows, the tangent directional arrows that's towards the circle. That indicates the direction of the object's speed or velocity. So let's look at that blue arrow that has acceleration on top of it. Let's say we decide to cut the string, or the yo-yo detaches from the string at this location where you see this red arrow right here. That's the direction that the yo-yo is going to go. Why? Because we're going counterclockwise as indicated by the green arrow. We're going to cut it off at this point. So the object is not going to continue in the circle because it's not no longer attached to the string. It's going to go in a direction that it's facing, which is where it's facing. This case, it looks like north because this circle is two-dimensional. But if you take an object and you spin it around in a circle and it breaks off, it's going to go in the direction that it was last facing. Okay? Let's look at another question. So we have the outside edge of a spinning CD is moving at a higher velocity than the inside track on the disc. Okay, so if you're not understanding that, let's look at people who are running on a track. You have somebody who's on the outside edge, and then you have somebody who's on the inside edge. So let's look at the radius of that circle. Okay, so whoever is on the innermost edge of the circle, they're closer to the center. So if anything, their speed is going to increase because they don't have much of a radius to cover. Now, if you look at the outside edge, their speed is going to be lower because you still have this big radius and you don't have a lot of force that's coming into it. Okay, so this is going to be false. The outside edge is not moving at a higher velocity. No, it's not. It is the inside that's going to be moving at a higher velocity. Okay. Another question, centripetal acceleration is directed towards the center of a rotating path. Go right back to the picture. And you see centripetal acceleration is where? Towards the center of the circle. So that question is going to be true.